and it is really my distinct pleasure and honor to be here, and I thank the selection committee for this opportunity. As Dr. Collins said, I will be speaking about this title that I call Democratizing Discovered Science with N equals Me. And as you'll see, this is an attempt to begin to ask the question, how can we be more inclusive in getting individuals that are traditionally underrepresented in medicine, in research, to be more social sciences, behavioral science, and as a cardiologist, I'm straying a little bit far afield, so clearly I needed a lot of collaborators. So I really welcome you to critique this work and give me your honest feedback. In terms of my disclosures, I have a patent with my work at Morehouse School of Medicine that focuses on a system and method for chronic illness care, and it is also in a tech transfer faculty startup in collaboration with Morehouse School of Medicine. So I would like to be able to just remind us, and I know all of us in this room are aware of that at NIH, in terms of the challenge of diversity and inclusion in clinical trials, and certainly in the new initiative with precision medicine that would involve 1 million person cohort. So we will have an opportunity with mobile technology, especially as we look at the engagement of minority patients in underserved populations. There's also now the new research that's allowing us to link behavior change to clinical research participation, especially when we're talking about chronic health management, as you'll see. I'd like to introduce this concept of P4 Women's Health, which is a predictive, personalized, preventive, and participatory process that's making its way into our intervention. And of course, as Dr. Collins mentioned, I am interested in how we integrate NIH research networks, and a number of them at minority institutions, our collaborating partners, as we approach this difficult question of addressing health equity research. So I want to begin where I really started to have these kinds of ideas, at the bedside or in the community. This is FNO. She's a 76-year-old woman with hypertension, diagnosed with diabetes in November of 2011, and at that time, her hemoglobin A1C was 11. She was soon introduced to Frankie as a health coach, and this is in the context of a research program that's sponsored by our CTSA at that time. This is the Atlanta Clinical Translational Science Institute. 6 months later, she had lost 45 pounds, which is how you see her now. Her A1C is 5.5. She is off metformin. Blood pressure is 116/69 on 2 medications. She monitors her blood pressure, blood glucose daily, and tracks her activity as she walks 2 to 5 miles 6 days a week. So what you see there is essentially the data that she gets back. So the monitoring process is actually using the type of phone that she has in her hands, which is an Android phone. And the blood pressure devices are on the HealthPulse platform, so they can come back in a synchronized manner to the phone. She's able to track it over several months or weeks, depending on her appointment schedule, able to respond. And when you look at the blood pressure graph there, you see it's color-coded in red, yellow, green. That just allows her in a very quick way to know whether she should act or not. And then when she shares the data with her doctor during the visit, it allows for a more effective clinical encounter. So clearly, this technology is becoming more common. The problem is a lot of the individuals that are using it tend to be those that are relatively well or just want to be physically active. We're having a challenge getting it in the hands of individuals that have chronic illnesses. As you know, chronic diseases are the leading causes of death and disability in the United States. And we are talking about heart disease, stroke, cancer, type 2 diabetes, obesity, arthritis as the more common ones. And obviously they're quite expensive. But interestingly, as we look at the numbers of adults affected, around 117 million people with at least one chronic disease, and recognize that clearly there are some behavioral risk factors that are associated, commonly
and how that may relate to therapy of human diseases, including cancer and neurodegeneration. Now, in my first talk, I'm going to give you a primer on the ubiquitin proteasome system, and important for this part of the talk is the idea that protein degradation is an essential function in eukaryotic cells. And so what I've depicted here are 2 different cell types. I have a neuron and a muscle cell, and these cells are distinguished by the fact that they have a different set of proteins at steady state. That's what's referred to as their proteome. And they have a different set of proteins because they are producing different proteins and they are degrading different proteins. And so protein degradation plays an important role in sustaining the different proteomes that these cells have. And it is the proteomes that makes them different. You can see, obviously, from looking at them, that a nerve cell has a very different morphology than a muscle cell. It also has a very different biochemistry, as well as performs a very different biological function. And at the root of those distinctions are the fact that these two cell types have very different proteins due to different rates of protein production and protein degradation, even though they have the same set of genes in their nucleus. Now, as I said, you have different rates of production and degradation. This is just showing a hypothetical cell. And when you look at a cell, you might think, gee, that's a relatively static object and there's not much going on. But in fact, new proteins are constantly being made, and to make room for them, existing proteins have to be degraded. And I just have a little animation here showing proteins coming and going, and this is really what's going on in the cell. It's not static at all. Now, if you block the degradation process, what would happen is you'd upset this balance, and unstable proteins would differentially accumulate. And that's shown here, where the red proteins are unstable, and so they accumulate to a much higher level when all of a sudden you now upset this balance of protein synthesis and degradation by blocking degradation. Now, people always ask me, why is it that there's so much protein degradation in cells? Why can't you just use some other mechanism to control things? It seems very wasteful. And this slide, which I cribbed from the Albert's textbook, makes what I think is a very important argument for why protein degradation is such a common feature of eukaryotic cell biology. And what this was intended to show in the textbook is why second messengers are unstable. But the same idea applies to proteins. And so what's shown here is how fast you achieve a new steady state if you have a tenfold repression in the production of something or a tenfold induction in the production of something. And what you can see is that the attainment of a new steady state is a direct function of the half-life. And so if you reduce the synthesis of a protein by tenfold and it has a 200-minute half-life, you can see it would take a very long time to achieve the new steady state down here. Whereas if it has a 1-minute half-life, you achieve the new steady state very rapidly. And although it's maybe less intuitive, the same is true if you abruptly induce the production of a protein by tenfold. And so if you want to use regulation of transcription or translation to control a